Okay, today we are going to talk about magnetic levitation and go into a little bit into depth on the topic of the science behind it, and the history, and the potential for what it can mean for us in our daily lives and in the world. So throughout life and in this class, we've learned a little bit about magnets, and we've come to understand kind of some very simple basics, like what things are magnetic, like tools, iron filings, the refrigerator, paper clips, and things that aren't magnetic, like a wooden block, a flower, a frog, or Dr. Delacourt. But this is a very simple approach to magnetism, just things that, stick together. And there's a lot more behind it and a lot more than just one very, overarching magnet principle. And there's actually a couple different kinds that I'm going to go into today. The first being paramagnetism. And this comes when, in certain objects, there's unpaired electrons, that as they spin, they have a magnetic field because they're charged. But these weak magnetic fields, they all go different directions, don't really do anything, and have no consequence. But when you line them up, or when you put this object into an external magnetic field that's larger, it creates an induced internal field with these electrons, and they all line up and create their field in the same direction, parallel with that external field. So you get kind of a greater magnet than before. And this kind of causes levitation, similar to like putting the same pole of two different magnets together, where you get that repulsion, but it's not stable. As soon as anything changes, it'll slip and go back to regular, magnetism, north and south sticking together in a similar fashion with paramagnetism. And the other kind is diamagnetism, which it comes from paired electrons floating around and still creating those magnetic fields, but they all cancel each other out, similarly to that paramagnetism, so there's no net magnetic field. But again, when you throw them into a larger magnetic field, these shifted and all over canceling out fields, they'll line up and they'll actually oppose the external magnetic field. The induced field will be the opposite direction, and this can be strong enough to repulse gravity even, and cause that magnetic levitation that we kind of can understand basically and think about and see in some basic objects. This idea has been around for a really long time. People have thought about it for hundreds and hundreds of years, but the science didn't really quite catch up with this ideas of thought. One of the first people to kind of postulate and put things down, his name was Samuel Earnshaw, and this is a great picture of him with some lovely sideburns. He came up with Earnshaw's theorem in 1842 that said there's no stable and static configuration of levitating permanent magnets. So basically saying that there's no magnetic levitation possible. Because at the time, any magnet was permanent magnet. They didn't really have the knowledge of electrons and the floating around and the offered Earnshaw. There's just no such thing as floating magnets, so we couldn't get this cool infinity gauntlet. But in 1939, this German physicist Werner Braunbeck did some research and was able to make bismuth and graphite levitate diamagnetically, which was super cool, super cutting edge for the time. But this kind of got swept away, forgotten about for a long time until more recent decades, when people were able to look into it more, think about it a lot more, and come up with even better ideas and ways to use it. But this showed that Earnshaw wasn't completely right in saying that there was no opportunity for magnetic levitation. Braunbeck was able to show that diamagnetic forces exist and can cause this opposite repulsion and create levitation, which was pretty cool. I'm going to go into the math of this now. This is where it gets a little bit more complicated and not as much fun and factual and interesting, but it's still important to understand why it's working. So this is the equation in one simple way to make things, to see how things would float. So we have B, which we know is the magnetic field, and then multiplied by dB over dZ, which is just saying the change in that magnetic field vertically or all around. And so it's just how that, as the object is in there, how it would be moving and change as it's going throughout that field, is equal to mu, which is that permeability of free space, times rho, which is the density of whatever the object you're putting in to that external magnetic field is, times gravity over chi, where the acceleration of gravity, which is negative 9.8 meters per second here on Earth, and where chi is the magnetic susceptibility of that object, or like how much that material can become magnetized in an applied magnetic field. So it's basically just saying like what it takes to magnetize that object and how magnetic it would become. And to be able to get things to levitate, these sides need to be able to equal each other. You need to balance it out so that there's no difference, and bam, you'll negate gravity and get cool floating things like this little floating frog inside of the solenoid coil. He's just been put inside an external magnetic field that causes his electrons to all line up opposite of that and fights against gravity. And this doesn't hurt him, doesn't do anything bad to him, just floats in there. It looks like he's kind of getting thrown around. Some potential applications for this are first Maglev trains that uses the magnetic levitation where it's on a track and the magnets cause it to be able to propel it forward, but there's no friction, so the train can go a lot faster. You're not using any fuel, so it's potentially better for the environment. Some problems we have with it, in other words, really costly to get the power source to be constantly going, which can be a little bit inefficient and cause some problems there, but there's a lot of potential for this if we can narrow it down, make it better. Additionally, we have zero gravity research, which using like small frogs or even small mice, we can test how that being in zero gravity affects them over a certain amount of time, and then we can extrapolate that out to people and show what can happen to people in space without having to actually spend all the money and resources to get people to space. We can't yet, though, really test this on people. You take massive amounts of energy. Like this says, you need a 45 Tesla hybrid magnet. So just a huge magnetic field along with 1 gigawatt of continuous power and a magnet in space big enough to put a person in. So it's really not practical or possible quite yet to magnetically levitate people on Earth. But, who knows? Science is always improving and increasing. Maybe someday we'll find a way to do that. And that is all. Hopefully you learned a little bit more, understand a little bit more, and appreciate the intricacies of how electrons can make things float. Thank you.